In this lecture, I'm going to go over 3 homework problems, one from this section on line integrals, and 2 from the section on Greens Theorem. So we want to calculate a certain line integral here, where it describes to us what C is. It's a line segment from 1, 0 to 0, 1. And for part B, we want to go ahead and find the value of the same line integral, but with the curve in the opposite direction, going from 0, 1 to 1, 0. So let me deal with A first. We need to write C in terms of a parameter t, say. And so we're going to rewrite x and y in terms of t here. And since C is a line segment 1, 0 to 0, 1, we do that, as you will recall, by taking a vector from 1, 0 to 0, 1, and using that to do our usual equation for a line. Let me get caught up here in this screen. So I went ahead and computed the vector from 1, 0 to 0, 1. So I have minus 1, 1. And to get the equation for the line, we would normally take a point from the line and use this vector as the coefficients of t. Well, to get the equation for a line segment, you want to be careful, at least if you're going to do what I'm saying, and take this point. It's the particular point you're starting from in this line segment and going to the other one. So the one you're starting from. So you took a vector from here to here, use this point. So I'm going to go ahead and use that as my point, and this will be my vector. So x will be 1 minus t, and y will be 0 plus t. So again, x is 1 minus t, and y is t. And as long as you do what I just said, you can always take t from 0 to 1 for a line segment. So what did I just say? Again, we use this for our point. We took the vector from there to this other point. And these will be the coefficients of t. And the constant terms of x and y, we have a 1 and a 0, applied 0 here, a 1 and a 0 coming from the point we started with. Okay, so that's our equation for our line segment. Now what we want to do is to use that to figure out this line integral, and all we do is we plug in what x and y are. We have x and y here, dx and dy. Well, dx will be minus dt, and dy will be dt. So we have everything we need, we just got to plug it in, and t is going to go from 0 to 1 in our limits of integration. And x, again, is 1 minus t, so I have 1 minus t squared there, times the cosine of y, which was t, plus y, which was t. So I have this expression, and now what I want to do is multiply this by dx. And dx, again, was minus dt, so I have minus dt. Put the dt on the outside, but I have minus dt. And for the next expression, we have x squared, which is 1 minus t squared. X was 1 minus t. Cosine of y is cosine of t, because y was t, and then minus t. And now we want dy. Since y is t, dy is dt, so we just have this expression, dy, which is dt. So we've just replaced x with 1 minus t and y with t and all this, and take t between 0 and 1. And now we're ready to solve this. We just want to integrate this. And notice the 1 minus t squared cosine of t is being multiplied by negative 1. And the 1 minus t squared cosine of t is just there, the plus 1. So these will cancel. This 1 minus t squared cosine t times negative 1 plus this. Then we have a minus t and a minus t here, so we have a minus 2t. So we're integrating minus 2t after we simplify that. And that's just going to be minus t squared for the integral, and we want to evaluate that from 0 to 1. So we're just going to end up with minus 1. So the answer to part A is minus 1. So again, that's the answer to part A. And what about part B? Well, here we want to go in the opposite direction. How can we go in the opposite direction? Notice when I plug in t equals 0 here, we're at the point 1, 0. When I plug in t equals 1, we're at the point 0, 1. So t going from 0 to 1 was telling us that we're going from this point to this point. At t equals 0, we're here. At t equals 1, we're here. So we're going from this point to this point. If I want to go in the opposite direction, we just need to go from t equals 1 to t equals 0. So in other words, I can switch these around. So if I just look at that and I switch the 0 and 1 around, that's really giving me what I want. I want to go from t equals 1. At t equals 1, we're at the point 0, 1, 0, 1. And I want to go to t equals 0, where we're at 1, 0. So I want to go from 1 to 0. Well, what does that do to what we just did? Well, before we had the integral from 0 to 1, and now we have the integral from 1 to 0. And remember that if you want to flip this around and go from 0 to 1, it's just minus it. So this integral is the same thing as minus the integral from 0 to 1. So it's changing our answer by a negative sign. So our answer now will be negative what it was before. When we had 0 to 1, we got negative 1. When we go to from 1 to 0, we're going to get a plus 1. So the answer to B is plus 1. So that finishes this problem on line integrals. Now I'm going to the section on Greens Theorem, and I want to do a couple of problems from these. So let's look at problem 3. So we're given a certain line integral, again, that we're trying to calculate, but this line integral comes back on itself. It starts at 0, 0, the origin, goes 1 in the x direction, then goes up 3, and then goes over to the y-axis at 0, 3, and then back to the origin. And it says it's going counterclockwise what we want, and that we're getting the whole rectangle. So we're just going around the rectangle in this sort of direction here. Okay, so our closed region that we're talking about is this rectangle. We have x going from 0 to 1 and y going from 0 to 3 in this rectangle. So 0 to 1 for the bottom part of the rectangle, and then y goes from 0 to 3. Okay, so let me go ahead and set this integral up. We're going to need Greens Theorem. So I'll just remind you what that is. And to set it up, I'm going to do a double integral over the rectangle here that we have. And again, x goes from 0 to 1 and y goes from 0 to 3 in this rectangle. So I just put x from 0 to 1 and y from 0 to 3. And then we need to do what it says in here with this integrand. We want to take the derivative of what's in front of the dy here, this, with respect to x. So we get cosine y minus 2xy squared. This will be 0 when I take the derivative. So we get cosine y minus 2xy squared. Then we want to subtract, the minus sign there, the derivative of what's in front of the dx here, this, with respect to y. So we get 0 for this part. This will be cosine of y. 3 will come down. I'll have minus 3xy squared for this part. So I get cosine y minus 3xy squared. So the derivative of this with respect to x, which was this, minus the derivative of this with respect to y. So that's what Greens Theorem is telling us, that I can rewrite this line integral as a double integral over the regions that's enclosed by C. And we get that for our double integral. So let's calculate this. Need some room, but we don't need Greens Theorem anymore. We used it. So let me put that away. And let's see what we have. We have a cosine of y here. We have a minus cosine of y. So those will cancel. We have a minus 2xy squared and a plus 3xy squared. So that's just going to be xy squared when I simplify. And we want to go ahead and integrate this with respect to y first. We'll have y cubed over 3. Y cubed over 3. 0 is going to be 0, but when I plug in 3, I'm going to have 3 cubed over 3. So 3 3's on top, 1 on the bottom. That's 2 3's on top, just 9. So 27 over 3, we'll just have 9 there. So this is going to be 9x. And when I integrate with respect to x, I'm just going to have 9 times x squared over 2. When you evaluate x squared over 2 from 0 to 1, you're just going to have 1 half. So it's 9 halves. And that's the answer to the question. That's what you get when you rewrite this line integral using Greens Theorem. So the answer is 9/2. For the second question on Green's theorem, I want to go ahead and use this problem. We have this line integral in front of us, and C is given to us in this parametric form. So let's look at what this is saying. Well, Green's theorem tells us to do something like this if we're in a closed region for our C here, to C enclose something. Yeah, so it looks like a circle. It's a circle. T is going all the way from 0 to 2 pi. But there's a little catch here. You need to be a little careful about what's going on in the circle. When I plug in t equals 0, I'm at 0, 1. So we're at 1 on the y-axis. When I plug in, say, t equals pi halves, I'm going to have 1 here and 0 here. So we're starting at 1 on the positive y-axis, and then we're going to 1 on the positive x-axis. Now let's see, we'll go to pi. When t is pi, this is 0 again, and this is negative 1. So we're at negative 1 on the y-axis. So we're down on the other side. And so it looks like we're starting out at 1 on the y-axis, going to 1 on the x-axis, and going down to minus 1. And if you keep going, it's going to go this direction. But notice that's not counterclockwise. Green's theorem is about a curve going counterclockwise. This is going clockwise. So when you're going clockwise, again, what this means is you have to change the sign, just like we did in the previous problem with line integrals. We're going the opposite direction, the sign changes. So we're going to get minus what we would with Green's theorem. So Green's theorem gave us a double integral for this. We want minus that. So let me tell you what we're going to end up with. So I put minus here. And Green's theorem has given me, for the rest of this, you're integrating over the region that's enclosed, which is this circle. Notice x squared plus y squared is 1. This is a circle of radius 1 centered at the origin. And then we take the derivative of this with respect to x. Now this is just 0, and this is just 1. So we're just ending up with 1 here. Minus the derivative of this with respect to y. This is 0 with respect to y. This will be minus 1. So minus a negative 1. So derivative of this with respect to x minus the derivative of this with respect to y. 1 minus negative 1. So we're ending up with 2 here. So we're just getting minus 2 times the area of a circle of radius 1 centered at the origin. So again, this is just the area of a circle of radius 1 centered at the origin. That's pi times 1 squared. So that's pi. And so this is just going to be minus 2 pi. So we get minus 2 pi for this answer. And that is the answer to this line integral when you use Green's theorem to evaluate it. Of course, it's the answer to the line integral, even if you don't use Green's theorem, but Green's theorem helped. So that finishes this lecture.